All right, this one's a 3-set Venn diagram. Let just have a look at that. I want to go ahead and start up the bubbles here. Okay, so I just started the basic framework here. We know we have 58 total. We know we have 21 in chemistry, 24 in physics, and 17 in bio. And you know there's got to be some overlap because these are way. If you add those up, it's way bigger than 58. All right. It says 5 take physics and chemistry, and I don't know. Yeah, this is a little bit ambiguous. Does that mean they could take all 3? Well, there's 2 taking all 3. This is kind of nice. I think that's kind of helpful. I know that goes right there. But when I see this, I think this should be written a little bit better. 5 students take physics and chemistry. That goes in, like, there's the physics chemistry overlap. Does the 5 include the 2 or not? I think it does not, if I remember correctly, when they made this problem a few years ago. I think this all means not both, but that's not clear. I think if this was a quiz or a test, you would have to ask that. Or if this was the SAT, I'm sure they do a better job. So that means on all 3 of these little statements. 4 take chemistry and bio. I think that means this. Otherwise, I think it adds up to more than 58 still. So that's the problem. But in general, they need to be better at that. Okay, so this is 3. So now I can fill out the rest of these zones, right? So this is the whole 17 who take bio who are not part of this group. So 9, this is 8 left, I believe. This is 24 minus these 10, this is 14. And this is 21 minus these 11, which is 10. Okay. Now, again, these should all be, oh, and I didn't figure out what was out here. It could add up to, 58 total. I'm not sure. This is 21, 35 plus 11 is not. No, it's not enough. So, okay, so again, we do that again. I'm just adding up all these quickly. I know this is 21. Plus 14 is 35, plus 3 is 38, plus 8 is 46. So there's 12 students out here, I believe. And that's what this first thing is asking about. Find the probability that C or U or P, sorry, C, that's not U, C or P or B, not. So the or thing here is like the whole big triple bubble, and not means outside of all of that. So this is the 12 out of 58. Okay. B given P. So P is the denominator, and that's 24. I wish they wouldn't use P, because P looks like that's P. All right, this is an event called P, but P stands for probability. All right, so of the 24, so just focus in the 24 now. How many of these are B? Well, there should be 5. It's those 5 right there. Out of the C's, well, the C's are the 21. How many of those are also B? It looks like 6. Of the B's, that's 17 of them. How many of those are also P? It looks like 5. Notice this one and this one, they just reverse the conditionality, but the numerators will be the same. What changes there is the denominator. The numerator of the given that is the intersection of the 2 things, and the denominator is based on, of course, just the second thing. So, all right, and then P naught, okay, who's in P naught? P naught is the 10, the 4, the 8, and the 12. So that is a total of 20, 34. Of all those that I just counted up in those zones, how many of those are in C? The 4 and the 10. So that's 14. Okay, hope you enjoyed that. 4 Venn diagram set is really hard to draw. It seems like it should be 4 circles just kind of in a square pattern. It's really not. It's a very hard thing to draw, actually. Okay, last section. Drawing 2 cards with replacement. What's the probability of the first card is a heart? Well, that's easy. That's 1/4 of the cards, or 13 out of 52. What's probably the second card is a heart, given the first card was a heart? All right, so I made a mistake. I had to go back. Okay, never mind. I did all this wrong. Sorry if you had to see that. No, you didn't. I don't know if you saw any of that or not. I think I went back and edited this fine. All right, this is with replacement. With replacement makes life really easy. Okay, so with replacement, that's fine. What's the probability that the second card is a heart, given that the first card was a heart? Well, who cares about the first card, right? This is with replacement. So the first card happens, it's a heart. No one cares because we put it back in. And now it's probably the second card is a heart. It's totally unrelated and independent to that. It's still 13 out of 52. This is the original deck again because I replaced the card. What's probably that both cards are heart? Well, we just have to have that thing happen twice. 13 out of 52 times 13 out of 52. So knowing the without replacement stuff is really a nice thing. I mean, it's really a huge thing to pay attention to, with replacement and without replacement. If you don't pay attention to those, yeah, you get totally different answers, which I just noticed when I got here and I went, oh, wait a minute, it's different. Okay, so 2 cards are drawn without replacement. What's probably the first card is a spade? I mean, they could have done this again with hearts, but it's the same. It'd be the same probabilities. What's changed here is that now we're without replacement. That's the big deal. First card's a spade, well, same. We still have 13 out of 52 spades. What's the probability that the second card's a spade, given that the first card was a spade? Well, if you've taken out a spade, so this is just the conditional probability about the second card. And now we're trying to draw this second card after a spade's been removed. There's only 51 cards in the deck, and only 12 of them are spades. So what's the probability that both of these things happen? That's different than asking the question in B. It's this has to happen, and then within that realm of possibility, this has to happen again. And because I just calculated this, I know what this answer is. It's 1 out of 17, which is really close to the first answer. I mean, 52 is a lot of cards, right? And things don't change a lot, but they do change. Instead of 1 out of 16, it's 1 out of 17. I think that's really kind of nice how that works out. Okay, we've already gone through this. Actually, this was from 3 or 4 lessons ago when they defined this whole thing, that when you can multiply things that are not independent if you adjust for that in the given that probability here. If you rearrange this equation by dividing both sides by the probability of A, that shows you here what we've been doing all along. We've been finding these conditional probabilities. I kind of have a problem with the way this whole thing's written out. Sure, if it's independent, you have to do it this way. But if it's dependent, this doesn't mean that, I'm trying to say, this second one is a general rule. So this is the general multiplication rule. This works whether or not, that doesn't look like it says general, but this works whether or not they're independent. It doesn't have to be dependent for that to work. But if they are dependent, you have to do it that way. But if they're independent, it will work, because if they're independent, it turns out that these two things are actually equal. That will probably come up later. But if they're independent, those things are equal, so it doesn't matter. So you can always apply the bottom rule, but the bottom rule is kind of a pain if you don't have to do that. The top rule is easier if you know they're independent. Anyway, there's nothing false about this. I think it's a little just misleading because the second one is actually the general rule that works all the time. If you don't know if it's independent or not, use the second rule and you'll always be okay. You don't have to know that it's dependent for that to work. Okay, here's Vera. She has M, B, and this. So determine this. Now, I don't know if I need to make a whole Venn diagram or not. It's just going to be the probability of M from the last thing we just did, M and B over the probability of B. Or like we've been saying, when you have to figure this out, put the probability of B on the bottom. And if you have a Venn diagram, we're looking within this 18%. Well, I guess I can't see it because I don't have a Venn diagram. But I do have the and. So the and is just right there. That's fine. I don't need you to simplify that. That's 5 out of 18. That's fine. Tree diagram. Okay, this is when probabilities are affected by previous outcomes. So 5% of the bags contain forbidden items. So there's a 5% chance that a randomly selected bag has a forbidden item. That's a scary high percentage. 95% of them don't. But if this is about screening for that forbidden item. If it has the forbidden item, there's a 98% chance that the alarm's going to go off. That's still kind of low. I wish it was higher than that if I'm going to be on an airplane. This one, if it doesn't have forbidden items in it, it still triggers the alarm 8% of the time. So this is like a false positive, and this is like a false negative. We will probably talk about that some more. This is a common thing to have to do for tree diagrams. We use these in AP Stats all the time. Okay, so complete the tree diagram. Find the probability. Oh, I should probably finish the ends of that. I'll do that now. Okay, so like last lesson, I just multiplied straight across. And I got these probabilities, and these should add up to 100%. Notice also that these two probabilities add up to the 5%, and these two probabilities add up to the 95%. That's probably not a surprise. Okay, so find the probability that a randomly selected bag contains a forbidden item, so it's in this path, and triggers the alarm. Okay, it's just this. It's just the 0.049. I can get that right out of one of those ends. Find the probability that a randomly selected bag triggers the alarm. Okay, that's these and these. So I have to add those up because they are mutually exclusive. I can add 0.049. I'm doing this in another window, and 0.076. I guess I could say I'm doing that here. 0.049 plus 0.076, and I get 0.125. Given that the bag triggers the alarm, this is 0.49. Sorry, let me fix that. Yeah, I just couldn't read it. And yeah, this is we do this in AP Stats all the time. So given that it triggers the alarm, so out of these two possibilities, what's the probability that it contains a forbidden item, which is this one? Like, what's the probability it's this one out of these two? In other words, what's the probability it's from the 0.049, you know, the correct positive ones out of all the positive identifications? And so that's kind of an interesting probability to know about. Let me calculate that. This is 0.392. So this is, okay, given that a bag triggers the alarm. So this is every time the alarm goes off. This is really the probability that it's actually got dangerous stuff in it, because there's so many false negatives, like 2/3 of the time, or sort of, right, that we've got these false negatives in the way. So it's only this percentage out of the alarm time. So knowing the alarm goes off, there's still like a less than 40% chance it's actually got harmless materials. This is called, well, it's conditional probability, and a lot of people don't quite understand that. We'll talk about that more in the Zoom class. 6-sided die with 5 faces marked A and 1 B is rolled. A ticket is then selected. If jar A contains 2 pink and 5 green, jar B contains 4 pink and 3 green. Oh my gosh, I need a tree diagram right now. So they didn't exactly say this, but I'm guessing when you pick you roll an A, that means you pick something out of, jar A. So all right, so that's the tree diagram I got. Let me finish out the ends. Okay, we are totally gonna make this in time. Probability of the pink ticket, and it was from B. So B and pink has to be the 4 out of 42. It's nice that these denominators are the same in the 2 jars. Probability the ticket was pink. Well, that could be these 10 or it could be these 4. So that's a 14 out of 42, which reduces nicely, but I won't do that here. Ticket was chosen from jar B given that it's pink. Okay, so out of the 14 possibilities, or the 14 out of 42, but out of the 14 possibilities that it is pink, how many of those came from B? Just 4 of them. Now, I could have called that 4 out of 42 divided by 14 out of 42. I would have gotten the same thing. That actually works either way. All right, here's another big situation. I'll let you read about this in subsequent screens. Classic old marbles out of a bag. I don't know why they're having us do this at tree diagram, because this is just as easy as the ones we did before where we didn't need a tree. Anyway, probability that the second marble is green. You might be thinking, well, the probability the second marble is green kind of depends on the first one, right? It's either 1/5 or 2/5. Well, yeah, that's why we have this whole thing. Probability the second marble is green happens here and here. That's a total of 10 of the 30 outcomes, because those don't overlap. I can add those up. Of course, it's 1/3. Probably the first was green, given that the second was green. So out of those 10 where the second's green, how many of those have a first one that's green? It's just these here, the 2 there. So 2 out of the 10. Okay. Kate spins 2 spinners. Create a probability model to represent this this situation. Yeah, should we do Venn diagram? Should we do a tree diagram? Well, we're going to spin 1 spinner, and then we're going to spin another spinner. They're independent. It's kind of like there's 3 outcomes for this and 4 outcomes for this. There's no kind of, the overlap seems kind of weird. This to me feels like a tree diagram, so let me do that. The problem with the tree diagram here is that there's just so many outcomes. Yeah, I could do it this way. I could do it as a table, I guess. I don't know. Let's see how it goes when we get into the probabilities. First spinner lands on red and second spinner lands on blue. All right, so these are totally independent things, so I know I can just multiply these. First one's red. That seems to be a 1 out of 3. If those, I don't know, those areas the same? This looks like a right angle down here. If that's a right angle, and this thing, free to spin how it wants, that's 1/4, and this is 3/8 and 3/8. Oh, that's kind of cool. Let's do that. Okay, so red is actually 3/8. That's 3/8 of the circle. Yeah, I like this. I don't know if I'll match I'm a geometry person, so I don't know if this will match their key or not. They might have 1/3 for that. Those don't look equally likely to me. It looks like red's got too much, way more than green and that kind of stuff. All right. And the second spinner lands on blue. Second spinner lands on blue is 1/4. So those are that's independent. I go ahead and multiply. And yeah, I should perform this operation, right? This is 3 out of 32. Okay. First spinner does not land on red. So I like that being 5/8. If you look at the proportions of those angles there. And the second spinner does not land on blue. So that would be 3/4 of this area. That gives me 15 out of 32. Okay. First spinner lands on red or second spinner lands on blue. All right, those are, gosh, they're not mutually exclusive, so I have to kind of worry about how this works. So I'm going to do the probability of the first red plus the probability of the second one being blue, that's the second blue, minus the probability, I'll just say this, of both, right? Because I don't want to count that twice. First one's red. We already do this? Yeah, it's 3/8. Plus the probability of the second one on blue, and that's 1/4. What's the probability that they both happen? Oh, good, I already have that. So minus 3/32. I got to do that on the calculator. And I get 17 out of 32. It's slightly more than 50/50. Interesting. Okay. What's the probability the first spinner lands on green, given that the second spinner lands on blue? Well, given that the second spinner lands on blue means nothing, right? Because if these are independent spinners, knowing this doesn't change anything about this. That's the thing I was last telling you about, the independence definition. So the first spinner lands on green, that's it. I believe it's 1/4. Okay, and that's it. We made it in 3 parts. Okay, see you on Zoom.